Let's begin.
Let's begin?
Yes.
Okay, so let me first.
Take a picture of us.
So come out of this. I'm not taking picture just to see who is sleeping. Okay. That's not the purpose, okay? I just didn't have a chance to make a slide. I'm very sorry. So I'm excused. I became very popular during the final week among the students. So they took away all my time. So I just jot something down on this thing. So I'm looking at this phone or computer from time to time. Okay, first, let me begin the talk. So, title of the talk is this. Deciding the consistency of polynomial constraints over real prolongation and relaxation. Okay, there's a title of the talk: deciding consistency of polynomial constraints over real by prolongation and relaxation. Okay, so I'll just tell you my name. My name is Hoon. It's pronounced as Hoon. My first name, and this is my last name. And then the joint work with my PhD student, Brittany Y. Riggs. Okay, if you want to see her, I have a photo on my computer. I'll show it to you. So I brought it here because one of my main purpose of giving talk is to be a PR agent for my students. I try to always work. So please, I told her to take the nice photo, high resolution, so you can have it also. Okay, good. All right, so before I begin, okay, so thanks a lot for the invitation. Actually, I came here not for this talk, actually. I came here to work with Alexei and also Gleb on the identifiability problem, precisely, for differential modules. It's a wonderful topic, also a wonderful talk, okay? I really like the talk. I don't think so. Okay, but then he also asked me to give a talk. So I thought about what kind of talk should I give? And I really thought about this one. And then I said, maybe this one. Why is it so? It's because prolongation is one of the things we are very familiar with. Differential algebra, of course, okay? Relaxation simply means, just treating the derivative as a new variable, okay? That's it, okay? So, but I think not many of you maybe heard of doing something like that over a real number. Usually they over a complex number, closed field, or algebraic closed field. I here talk about the real closed field now, real numbers. So they might be a bit interesting, new. That's why there's a talk about this. Okay? Okay, so with that introduction, I will just now jump in to talk. Okay, good. Okay, so let me first briefly give you the overview first. Some overview. The overview of this talk. General topic overview. So, okay, so here we have a hard problem. Problem is hard, like differential equations. It's a hard problem. Okay? Learning the problems, hard problem. Now you want to make it easy, of course. That's what we're going to do in our life. Turn hard problem to easy problem that you want. Okay? So the question is, how do you do something like this? Well, one way to do that is, there are many ways to do it. many ways to do it. Okay, standard mathematical technique is always transformation, transform. Okay, what kind of transforms. Now, here we'll talk about this prolongation and relaxation. This is one way to do it. May I switch that direction to save space? Switch direction, okay, here. And then do an easy problem. Let's say if I'm okay, I'm out of time, okay, just tell me to stop. I'll stop in the middle of the sentence. Okay. It's because ongoing work. It's ongoing. Okay, so I can stop anytime. Okay. Now relaxation. Okay. Relax. Better now. Okay. Relax. So now prolongate and relax. That's okay. Verb match. Okay. Good. Prolongate and relax is the technique. So now, let me give you an example. Okay. You guys are very familiar with differential equation. Of course, algebraic. From now on, when I say differential, I mean algebraic. Okay. So you have differential equation. So how the problem? So how do you do it? Well, prolongate simply means what? Differentiate. We cannot differentiate. Prolongate. Relaxation means that you take these guys like x prime, x double prime, so on, as what new variables. New means independent. Okay? New variables. There's no algebraic relationships, okay? So it's indental, okay? So new variables, treat in that way. Then this guy turns into polynomial equations, which is easier, in some sense. It's analysis, this is algebra. So this is one way to do it, okay? So this way, of course, this work of the coach and read and all those people, differential algebra, okay? All those things. So don't go through that. You are familiar with all those things. Okay? Now, but then how about polynomial equations? You can say polynomial equations is still difficult. So what do? The same thing. Here, prolongation is not differentiation. It is multiplying by a variable. Like multiply by variable. Okay? That's not the only way to do it, but it's one standard way to do it. There's some other way to do that also. Anyways, if you do, and then you prolong it, and relax means that you consider things like, this kind of things, monomials. Monomials, okay, all those guys as what? New variables. Okay? If we just stop, then this guy becomes linear equations. So, how did you read differential equation? Prolongate, relax. Polynomial equation. Polynomial equation? Prolongate, relax. We get linear, and after that we stop, saying that this is undergraduate, high school. Finish right here. If you want to go further, actually you can go further here, which I'll not do, okay? That's it. So this is a already well-known thing or done, okay? Though maybe this might not be well known, some of you, so I'll give you a very informal review of this guy, okay? This one I will not do it. Now, today's talk, main talk is about this guy here. Polynomial equations or inequalities, but it's over R. Of course, it's over C. It's complex number, okay? So that's what we'll talk about. So this is a topic. This is today's topic, the main topic. So this is it. Now, to save space, I'm going to erase something. I have to save space. So erase this guy, okay? Very good. Open now. Okay, good. I'll just drop the names. Of course, this is a coaching seminar. I must say coaching, okay? Coaching here, right? This side, great names are Sylvester, and then Macaulay. Okay. The Sylvester gave this some result on that thing about 1830 through 70 to period of time. And Macaulay is 900 sometime. Okay. Now Sylvester is a great mathematician, you know. Just know that when you say word matrix, which I'll do that sometime, matrix, the word is coined by Sylvester. Graph, for example. Okay? Many great names, like discriminant is from Sylvester. He named them. Euler torsion function was named them. This can number theory, combinatorics, and whatever. Okay. Macaulay is also a person who was studying the so-called invariance theory. And in the process, he wrote a book, and then many other papers also. In the process, he generalized Sylvester work to the multivariate cases. Okay, that's what it's about. Okay, good. With that, now I'll go to the review of this guy a bit more detail. Okay, because it can be a good preparation for the over R. So here you go. Polynomial, poly equations over C. This review. This guy's review. Nothing new here. So polynomial over C. Now, for the sake of the simple presentation, I'll only consider from now on the simplest but meaningful examples only. And you can think about how to generalize it. You can do it. Sometimes it requires some more work, but still, you get the main ideas, okay? So the simplest problem, you can think of the following problem. Simplest but meaningful problem is you consider two polynomials, that's f and g, with a complex number coefficient in one variable. Now you have to decide. You have to decide the following question. There exists x equals in C complex number, so f and g are equal to 0 at the same time. I think it's the simplest example. Simplest example. If it's only one polynomial, obviously it's true. Okay? It's true. Over complex. So it consists two polynomials. Okay, so that's it. Okay, I'll give an example. My cheat. Okay, go. So I'll give an example. Since I'm lazy, I'll give you a very easy example. Coefficients chosen so that I can remember easily. Okay? And G, can you guess what would that be? Please guess. If you cannot guess the coefficient for the next one, I'll start talking. Please. Math is beautiful. That's the underlying principle. Okay? Okay, that's right. Okay, good. So I have these two f and g. Now I'll ask you a question. Answer, true or false? Go. Every time. True or false? It's true there's a common complex solution?
No.
No?
No.
How do you know?
Unlikely.
Huh?
It's unlikely.
Unlikely. Actually, if you choose f and g randomly, probability number 1, it is false. So your answer actually is not that interesting. It's only interesting when it says
But
yes.
it's
So surprising. So you are gambling when you are chance of winning 100% time. Okay,
Yes.
that's not really surprising. Okay, it's not really. So anybody else? Is it true or false? Okay, so how do you do it? The question is how can you do this thing? Right? So this is a question actually. This is a question already about 1600. 700. This question actually not 700. This question is posed, but it's coming along. Okay, and it's not so obvious. Okay, of course the brute force. So method one is brute force. Brute force approach is what? Find the root, all the complex root. Find all the complex root and compare, see whether there's anything same, right? That technique is miserably terrible. Okay, so you should not do such things. Okay. Now here I must do some dashing numerical methods. Okay. Actually, I love numerical method. Okay. but I'm just intentionally, I'm pretending to bash them, okay? So numerical method often, when you have this kind of questions, they actually find the solution, and then they look at solutions, oh, I see there's something saying, therefore, yes. So they do, okay? So that's the one reason why they have also supercomputers to find the solution for differential questions, PD, so that they can say about, oh, whether we have hurricane coming this way. Okay, find the solutions, okay? Now, the breakthrough results in mathematics due to these people was that basically, also question is that you can answer this question without finding the solution. So in some sense, there's a key. The key statement might be, we can say something about, or properly, you can say something about properly about the solution set without finding the solutions. I think it's a key thing. We can say about the properties of solution sets without finding the solutions. So the key is talk about solutions without finding the solutions. This is the key, okay? The key, okay? Okay, that's often that's much more interesting, elegant, also more economical in some sense. Okay, good. So here comes the Sylvester and later on Macaulay. So they came up with the method called resultant. Okay. So I'd like to have some quick overview on the audience. If you know resultant, could you raise your hand? Polynomial resultant. Okay, so that means okay, fine. Go ahead and raise your hand. I know that you know it, okay, please. Okay, then I will quickly explain. By the way, even though you know, today I'm going to explain resultant theory from the perspective of prolongation relaxation. That's the whole point. Okay, even known to start, sometimes a good idea to go back to the common sense and what? Look at it again from a different angle. That gives you an idea, okay? So remember this Albert Einstein said, quoting, not exactly, that all the major discovery in the human race, including his own, okay, that is a refinement of a common sense. Interesting. I believe it. Okay. So today we'll talk about the common sense, but we'll look at it again and refine it. Okay? And then they'll lead us to the overall. Okay, good. Let's begin. So resultant theory, what does it go? How does it go? The method goes this way. That let me give you a common, let me give you over here. What it says that, well, this idea is basically this one. Explain the idea. Explain the idea from the prolongation and relaxation terminology or concept, okay? Prolongation and relaxation. Something's wrong. Relax. Okay, so right now I have a polynomial f here equals 0, which is what here? X cubed plus x cubed plus 5x 7 is equal to 0, and 2x squared plus 4x plus 6 is equal to 0, which we have. So this is what we want to decide, okay? Now, what Sylvester did was, he said, let me look at this sentence now here. 4x and then c, and then copy this guy. Same thing. Copy the same thing. Okay? And then copy this one. Same thing. Copy the same thing. Okay? Same thing. But, okay? But he add one more, namely, multiply this guy by x. Then it becomes what? 1 over what? X to the 4 plus 7x. You get this one. That's right. Now look at this one. So again, same, this is the problem you want to decide. This is, this one, we just modify by adding one more thing here, which is obtained by multiplying this one by x. First equation by x. Now you see clearly that this guy is redundant because it's implied by this. So they're equivalent, clearly. Equivalent. Okay? So what is he doing? He's taking a problem, making it redundant. Okay? This is stupid. It's stupid thing to do, okay? Okay, you might say it's a lemma. It's a lemma. Lemma. It's not on you guys. It's a lemma. Okay? Good. Anyways, now he does the following. Well, now let us treat. Pretend that these guys are. Back up. I'm sorry, back up. And then he continues with this one. Continues this. Okay. By adding other guys. Okay. Now let me now from now use this notation. F equals 0 is first guy. G equals the next guy, right? This is not function notation. While we add those F equals 0, instead that let's add some more. Like this one, for example. And keep adding. Okay. In fact, doesn't add this guy. Anyways, adds this one now. X times G equals 0. And then add once more. X squared times G equals 0. Equal the equivalent. Okay. So why is he doing all these things? Is the following. You do this one so far. The next one, okay, then we'll see what. The next one is the. Now look at the arrow direction here. Now here is the last x. Now it's x is a vector. In C to D, whatever number it is. Okay. And now treat this f equals 0. Now f is 0 is that guy, right? But treat this f equals 0. 1 times x cubed as just new variable. Let's say x sub 3. And 3 times x2 and so on. 5x1 plus 7 equals 0. Okay? And do the same thing. From that here. Okay, now clearly this one implies this. Okay, implies this. Now what it says is that when you start look at this, this guy's a linear system of equations now. Linear system of equations. Okay. And then you can show this one. You can show the linear algebra. Well, look at here. You're gonna find you can write down. Okay. So linear algebra will be basically you do like this one. Rewrite this guy. Linear algebra will be 1, 3, 5, 7, 1, 3, something like that. Okay. Write down this way. 2, 4, 6. 2, 4, 6. 2, 4, 6. Here. X to 0, 4 to x to the, what is it, 5, 4. Okay? Equals it. That's what it is actually. So here is the vector x, x to the 4 and 1. x1 and 1. That's it. Where this now view as a x vector. Now this is the what? Matrix, square matrix times a vector, but non-zero vector because you want here, okay? Non-zero vector. So linear algebra so that this one has a non-zero solution if and only if determinant is 0. So this is if and only if determinant 0. Determinant is matrix and is 0. So it turns out to be it's not 0. I think I forgot the number. 120 something, okay, whatever. So it's not 0. This is not 0 actually. Okay, turns out to be. It's not 0. What happens? What happens now?
No solution.
No solutions. You can go backwards. No solutions. This is what it is. No solution. That's right. Okay, so now prolongation and relaxation thing. Where are yellow colors? I lost my yellow color. That was clever for us. Is that yellow color? So this is the prolongation. Prolongation. This process is a prolongation. This is a prolongation. And this is relaxation. Relax. Okay. So you do prolongation, keep adding redundant statement basically, lemmas. Keep adding things. You don't need it, but keep adding it after you relax. The point is the following, that sometimes you can do this one by prolong enough and relax, what happens then? You get this one. This result, which is great. Now, but what about the other direction? Is it also true or not? That's the question. It's true or not? No, that's not always true. Okay. For instance, okay, suppose that we just relax right here without prolonging here. Then of course what? As a linear system here, after relaxing, this has a solution. It's got a solution, okay? So this direction is not obvious, okay? You cannot say, okay? So there's a question. The question becomes, so the question arises here. So it's a question. The question arises, is direction also true? Okay. The answer is, the theorem is like this. Sylvester also, theorem is that, yes, this one, yes, if what? Prolonged enough. Prolonged enough. Just like differential case. Prolonged enough is true. So if it's prolonged enough, then do. I think if I say intuitively what's going on is the following. These monomials, x cubed, x squared, x, and those things are dependent. They depend on each other. Here we treat them as what? Independent. So you're losing information. But still can go backward if you prolong enough. What that means is that prolongation is somewhere capturing the dependencies sufficiently. If you prolong enough, you capture dependencies sufficiently, and therefore you can relax it without danger. So this is what's going on inside. Okay, so theorem first theorem is that what? If you prolong enough, then if and only if, that means you capture enough information. But the question again arises is what? How much is enough? This is basically it's non-constructive proof, actually. Now I'm going to give a constructive proof. Then you have to actually find the bound on the number of prolongations, and Sylvester actually gave it. Sylvester gave the result, the theorem. Sylvester's theorem says that you have to prolongate. Prolongate means how many more things you have to add, right? Exactly that if I give the name here, this is a degree, the degree is mu. The degree, let's say. Then, okay, first by the number of prolongations is this one. Mu minus 1 plus mu minus 1. Okay? There's one way to say if you prolong this many times, that's fine. All right? Actually, Sylvester did not state this way. Sylvester stated in terms of degrees. Okay? But then anyways, then you can go backward. So these are the results.
I have a question.
Yes?
So how is this conceptually different from computing the GCD of the tool?
Computing the GCD, how is it different from computing GCD? They are different, but they're related. Clearly, they're related. Right? Because computing GCD operation, okay, first, I talk about the operation or I talk about the concept of GCD? Which one? I mean, operation.
Well,
this one does not let you compute the GCD. Okay, so you have to find GCDs there. You have to compute something called the sub-resultant. Okay, so it's not actually GCD. Okay, but it's related. And also one more information: the one way to find the polynomial GCD is using an algorithm, polynomial remaining, and that can be encoded as carrying out Gaussian elimination on this matrix. This matrix. Okay, so they're related also.
and won't you be able to see that bound from GCD? From computing the GCD? That mu minus 1 plus mu minus 1.
That's correct. That's correct. That's right. Absolutely correct. It's okay?
Yeah.
Now, this can be also generalized to multivariate cases, and it's done by Macaulay. Again, this famous green book, or the Macaulay's green book, blue book. Okay, so, beautiful book. It's generalized fully to multivariate cases. except that there's small error in the Macaulay's actually presentation. He thought that this actually, if you don't live on the certain thing, turns out it is not true. That was corrected by a guy called John Kenny at Berkeley. And he was actually trying to solve a robot motion planning problem, pathfinding problem, and then he tried to use the Macaulay's result, and he found an error in Macaulay's thing. Macaulay has a small case where it's not always true. So he fixed it and became famous result. But I think he got the best PhD award from NSF in that year, something like that. Okay, that's my memory. Good. So this is it.
That's it. The talk is
No. This is the quick overview on the complex case. So can I go to now the real case with the remaining time? May I?
Yes.
Okay. Now go to the real. Now erase everything again here. Go to the real now. Okay. Now. Okay, I'll go to the real case now.
Why is this called a complex case?
Pardon me?
Right. Why is this called a complex case?
Because the question stated for deciding whether there's a common complex solution.
But what's the argument has to do with complex?
The argument has to do with the following: that the only way to go backward requires a complex number. Forward is not. That's good observation. Actually, forward observation. Okay, this arrow, you can choose any field goes through, but going backward must be algebraically closed. Thank you. In order to show that this bound is okay, that requires that. Okay, okay, good. Now I go to real. Okay, go. Begin. I'm not erasing, I'm just spreading the dust right now. You can see? Okay, good. Now, polynomial polys over real now. That's the actual main topic. So again, I will only talk about the smallest meaningful case, okay? But everything I said can be generalized to multivariate case, generalized, okay? With some work, sometimes hard work, okay? But I won't talk about the simple case right now. Okay, so what's the problem? For you, problem, let me consider this problem here. It's easiest, not easiest, smallest meaningful problem. One polynomial in one variable. Decide. Decide this one. There exists x is now real number. To make it interesting, positive real number. And then let's say fx equals 0. The inequality is hidden by here. So this is, I think, the simplest example you could think about over real. Now, okay, so I'll give an example. Example, let's say f is equal to x squared minus x plus 1. Please tell me yes, no. Yes? Yes? Do you say yes?
No.
No. You might mean. Oh no means what? You mean oh no on which one? Which sentence? No. No on your own response or which one? On both. On both. Okay, well in this case the same, right? So okay, so you can use the causally formula, right?
Yeah.
Answer is what? No. Okay? Which one? No. Answer is no. Good. But I will use this example, okay? Quick example. Good. All right. So now question is how do you do this? Okay. Question is how. How do you do it? Again, it's an age-old problem. Age-old problem, okay? I'll just drop some names, okay? Fourier, the famous Fourier transform Fourier, worked on it. Information. Descartes worked on it. And it was somewhere finalized by a guy called Sturm. Okay, so famous Sturm's theorem. And later on, the full generality by Alfred Tarski logician, the greatest logician of last century, Alfred Tarski, the Tarski-Banach paradox, or Banach-Tarski paradox, that name. But he's actually logician, okay, he's a logician. And Tarski, okay, the full-blown algorithm actually deciding this guy, okay? His main goal was not designing an algorithm. His main goal was showing that you can have a sound and complete system. Okay, this was a very, very important question at the time because maybe you heard about the Hilbert's program. Hilbert's let's axiomatized whole mathematics, formalize it, and then let's also find decision procedures, this kind of stuff. Okay, he was really happy to do it. And then comes the Gödel, saying that if you include the integer, well, you're doomed. Basically, roughly speaking, you cannot achieve both. Okay? So this is very disappointing. And then Task comes along and says that, hey, if you do over real number and algebra, it's fine. You can have a complete and sound axiomatic system. So his paper was originally called The Completeness of Elementary Algebra and Geometry, which means the algebraic version of real. Okay? So that's his paper. His goal was proving this complete. Hello, Gödel. You can have sound and complete stuff. Is it philosophically breakthrough? Okay, so at the time, philosophers write about this, saying, "Oh, Hilbert, we are just so happy," and then with Gödel, we just despaired. With Tarski again, we come back up. That's okay. And time goes by, I found out that algorithm is extremely time-consuming. They also went down again. Okay. Anyways, so this is it. Okay. Good. This is about year about 1930s. In case you want to read about Tarski's paper, in 1930, please read 1930, written by Tarski. There's another paper by Tarski, not written by him. 1950, a guy called McKinsey actually wrote it. I cannot spell his name. McKinsey, I think. I'm sorry for spelling, okay? I remember spelling, okay? So, McKinsey wrote for Tarski, 1950. And this one, please don't read it. It's impossible to read. This is easy to read, okay? Because he explains the idea. He wrote this paper so they can program it on the then computer, which is the drum. And the drum is the main memory. Okay, good. Anyways, this was my future device, by the way. Tarski, no, not Tarski, the next person. Okay, I'm not that old. Now, George Collins in 1975, around that area, he improved this method, dramatically using a completely different method. Okay, and I'll talk about it. So complexity here was a 2 to the n, and it's number of variable. You cannot give a bound on this tau of height. It's not elementary, okay? Task didn't care about this complexity. That was why this go, okay? And then Collins shows that this can be done to the n, double exponential. So you reduce the height of, let's say, infinite to 2 double exponential. And then time goes by. People call the Kenny, I mentioned Kenny and Renega, okay. So then in the around 90s, they showed that you can be reduced to the n single exponential for problem like this in general, okay? Okay, good. Now, then what am I going to talk about? I'm going to talk about the problem that we are the decision procedure.
I have a question.
Yes.
What is n in your problem?
And here, n is 1.
Thank you.
That's right. So this is
It's 2 steps.
That's right.
So you can do it in 2 steps.
Actually, I even know the other factors like number, coefficients of size, and stuff like that. Okay.
Okay.
That's right. Good. It's not 2 steps. It's not counting steps. It's the S4 notation. Constants are all you know. Okay. Good. All right. So now what I'm going to do is I'm going to go back to the one variable case and re-examine from the prolongation and the relaxation framework. Okay, that's what I'm trying to do. Why do such things? First of all, why not? Why not? Okay, new idea. Okay, look at same thing again once more. Okay, that's one way. I spent all my time, okay, many years on that thing. Okay, so it's time for me to stop doing that thing. Okay, so now prolongation relaxation approach. I'll talk about it. Okay. So let's talk about how to do that kind of prolongation relaxation. So I'll give an example here. This is a prolongation relaxation approach. Prolongation and relaxation approach. I'll give you two examples. Oh, I left two examples right here. That's great. Let me use an example, okay? So how would you do something like this one? So let's try, okay? So I have here what? Here on this side is right. There exists x. Real x squared minus x plus 1 equals 0. We know that is false, but pretend that you don't know. Okay? Let's continue. So what would you do? What would you do? We'll prolongate. But first, let's not prolongate. Let's just pretend that this is now, these are what? Independent variables. That means you view this way. Okay? There exists what? X factor now, which is in R square. And then this is becomes x2 and x1 plus 1 equals 0. Okay? Is it true or false? This one. True, of course true, right? So then, so not good. We lost information. We lost information. Okay? By relaxation. Lost too much information. You get the wrong result, wrong answer. So what do you do? Don't do it. Okay? And so what you do is that let us prolongate. We prolongate now. X squared plus x plus 1. Keep it as it is. Prolongate. Multiply by x. Multiply by x. And you get that, right? Okay. Now let's relax it now. We relax again here. Relax. It becomes now r plus, now how many variables are there here? So x2 minus x1 equals 0 and x3. Okay, so this is what? How many variables? 3 variables. Got it. Okay, now please note that these two are equivalent right now. Equivalent. Now this is this way, okay? Clearly. I'm asking a question. Is it true or false? It's linear. Hello, linear.
That's false.
Yes?
That's false. I mean, there's
But please don't guess. You know that it is false if you say.
No, but because x2 minus x1 is negative.
He already did it. He already did elimination over positive numbers. Did you do positive number? Right? Should be careful, okay? So you cannot do simple Gaussian elimination because it's. Be careful, okay? Anyways, okay? Good. So this is false now? Is this false? Okay, so now, again, I'm assuming that this can be done easily nowadays. Okay, for example, you can use about, basically, this is nothing but basically linear, the operation research thing, okay? Simplex and those things, integral method and those things. That way, okay? So it's a false, it's a false. Again, this is a prolongation. Prolongation. And that's relaxation. So it seems that this is okay. It seems to be okay, right? So now, but then this method is not useful unless what? This is also true, right? This direction. That's a key. Is it true that it's like this? In other words, the question is that is it true that if you prolong enough, you get capture enough information on the dependencies on the monomials, so that this if and only if, even after relaxation? That's the key. We capture information through the redundant stuff, okay? And then later on relax it. But redundant stuff is carrying the information, okay? Enough information. Is it true or not? Okay? That's not obvious, actually. It's not obvious, okay? And here comes again the question. Again, question is this direction, okay? And here's a theorem. I have a date. I forget the date. I'm going to get the date. Okay, actually. So, theorem. Okay, it is, again, yes, if prolonged enough. prolonged enough as a theorem. It's true if it's prolonged enough.
So whose theorem is that?
Actually, this theorem is technically theorem of me and my student Brittany Riggs. Okay. However, I don't want to claim the credit for this because the proof is actually mainly based on some other result. Okay, which is given a totally different context. Okay, but related again. So that is the proof. I'm talking about the proof. Proof is based on. By the way, you will not find this theorem stated in the literature, in the web. You will not find it. Okay, right? But you might find this one. It's based on G. Polya, a famous guy. The this way. I forgot. Okay, this way. Polya. Polya's wrote a very fundamental document in 1920. I forget now. What is it? What year was this? 1920. My computer's down. Now I got my cell phone. He has been sleeping from the beginning, so I don't care. Okay. So when I talk with him, he sleeps often. So next time I will sleep when he talks. I'm kidding. My colleague, okay. My colleague, dear colleague. Okay, good. Here comes.
But can't we treat this like as just linear recurrence of constant coefficients? Because it's
Linear recurrence of constant.
coefficients. Because if you would prolong, you will get sequence as kind of. This what you mean by poly?
No, it's not that one.
Ah.
But what you're saying is actually strong connections. Later, okay, you'll see, okay? Thanks a lot for pointing out. That's exactly what it is, okay? So in I forgot about the year, okay? I write down the year because this year is more important, let's say. Write down the year for you. How many minutes do I have?
I decline to respond.
You decline to respond. Okay, fine. This is interesting. Okay, so here goes. Okay, here comes. 1928, correct. 1928. Okay, Polya proved the following theorem. Actually, Polya proved much more general version of this following. Okay, I'll state only specialized version. We prove the following. If f, okay, if there does not exist x over real positive f equals 0 implies that there exists, let's say p natural number such that x plus 1 to be p times f as no sign variation. No sign variation. What does that mean? It shows that if polynomial f has no positive real root, then there exists some number p. That if you multiply this one to f, the coefficients all have same sign, which it proves. It's a remarkable theorem. It's one of the actually breakthrough results in real algebraic geometry. Okay? One of the cornerstone. Of course, not this particular one, but generalized version. It's a cornerstone of real algebraic geometry. Okay, so and using this theorem and doing some other works, you can prove this theorem. It's okay with you? I'm not going into any more details.
But is this the first known method to answer that question?
This question,
Yes.
as far as I understand, this question is the first time asked, actually.
No, I mean.
So therefore, it's the first time answered.
So, let's go back to the origin, to the problem.
Yes.
Is this the first solution to this problem or not?
No. You mean deciding whether this is
Not for this example,
Then
but in
what?
general.
general? No,
Yeah,
no.
for
These
any.
are the world methods.
Okay, so this is, how should I put it? So these are old methods to decide on a more general class of questions, correct? So you're solving this very concrete problem.
Concrete problem is a particular univariate problem.
Right.
Actually, it's not true. Actually, I'm only giving one, explaining the idea, method for this case. It's simple.
Okay.
It's okay with you?
And what's the number P? Is it
Okay, so
understood?
now, P, there
Yeah.
exists P.
Yeah, is there a bound or?
Oh, okay. Polya did not give what P should be, doesn't give bound. It's again, it's non-constructive proof. Proved it, okay? Just a coaching did, okay? Something in the similar manner, it's non-constructive, okay? But this is again important result, okay?
Hoon,
Yes.
So, are you saying that your method will do any kind of quantifier elimination or any kind of?
No, only right now existential quantifiers. Existential.
Okay.
That's right. It means consistency.
Okay.
But object number variables and polynomials and inequalities and so on.
And if you apply those methods to this problem,
Yes.
will it do the same thing or it will do something else completely?
You mean the process?
Yes.
Completely different.
Completely different.
Yes, absolutely different. Okay. Otherwise, why would I work on such things? I told you I was working on this for a long time. I'm bored. And you think I'll go back and do the same thing? Okay. Look at me. Don't I look happy? I'm just kidding. Okay. Okay, good. All right, good. Now the question arises again. Question arises again. Question arises again. Okay, any bound on the thing? What? Bound. On what? On the P. It's again same question, okay? The rows, okay? I just told you the differential case, such a bound was found. I think if I understand, bound was actually found for the first time after Cochin's work. Alexei and you and Colette, you and
No,
no. Who was it? I forgot. No, you don't claim either. Anyway, somebody from here, okay, give the first bound for the differential case. If I understand, okay. If I'm wrong,
But Hoon, so it's
Yeah.
because you're talking vaguely about that question. So you're talking about differential case. What problem in differential case you're talking?
consistency.
Consistency over differential closed field, right? So
That's right.
Okay.
That's right.
Yes,
Exactly.
that's
That's right. Good. So, and then algebraic cases I told you was given by Sylvester and McCall in general, okay? Now here, the question is that can you find the bound P? And then here's I'll give you.
But if you're talking about quantifier elimination, there was a paper by Dimon Grigoriev.
No, it does not give you bound on P.
Okay.
No, that's a different thing. Okay, you talk about this procedure. There are many, okay? One of them is Grigoriev. Okay? Right. Good.
I mean, in differential case, for differential.
That's also right. That's right. That's right. That's right. Differential case also. Good. Now theorem. Here, theorem is. Let me look at the time. Oh. Okay. So. Okay. Theorem. Some theorem. Version 1. Okay. And theorem version 2. Now, theorem version 1, I'm not going to write down. It's complicated expression, very complicated expression. Okay. This is obtained by analyzing Polya's work. He gave a non-constructive proof, but you can analyze the paper and you can figure it out. And it's done by Power and Resnick. Okay, but it's complicated expression. I'm not going to write down. Okay, all right, whatever that is. Okay, and then here is the new one. Okay, this is the to me. So now, okay, here goes this way. The P could be chosen to be this number. Summation over pi. I first give you some elegant expression. Pi over theta I. Something like that. Now what's theta here? theta is the real, and then imaginary here. Then think about the complex root of f. Complex root of f and conjugate, non-real roots, okay? Suppose that is one non-real root here. You put conjugate here. And that's the theta I. So ith root, okay? It is ith root and this theta I. Okay? So I'm talking about it. So it says that you go over the all argument of the non-real root. Again, pi over 2, and this is it.
But like, does you count each root in pair of conjugates?
No.
Ah, so
Only one.
Only one.
Only one.
And
That's right.
upper one. The upper one. So
that's
that-
upper
that
one.
is from zero.
Upper one. That's upper one. That's right. Correct. It's upper one. Okay. That's right. It's upper one. Okay. Now, yes.
I don't.
So
Alpha i's are what again?
this number can be
There can be what? Several roots, right?
Of the pronoun.
For all the roots, for the non-real roots.
And what's this notation around?
This ceiling.
Greatest. Oh, the greatest.
Ceiling.
But
Yes.
can this expression be negative? Like if you have theta close to pi, then okay, it will be 0. Okay, it will be 0, not negative.
That's right.
Just sitting. Okay.
It's carefully constructed. Okay. Okay, good. So now I'll give you some comparisons here for this information. So as an example is that the f is x to the 4 minus 4x cubed plus 10x squared. For example, this degree 4 polynomial. If you apply this one by analyzing the Polяр's original paper and obtain something, that P obtains a Polyar. The P is 400 over 90. The polynomial is 490 times, okay? But if you use that one result, okay, here, this is 3. Prolongation. It's improvement. Geometric improvement is true for in general, okay?
And what about sharpness?
Huh? So now, final thing. Thanks a lot. Okay. Question: how good are they? Right? How good? How good?
But is it also easy to compute this number?
Okay. So now talk about that later. Okay. Talk about this one. Theorem. Okay. Oh boy. Sorry. Okay. Theorem is that it is optimal. Optimal. Okay, when it's optimal, must always make it clear. Okay? Optimal among the angle-based ones. Angle-based ones means that look at here. This expression does not talk about the magnitude of the complex roots. Right? Okay. Amazingly. So this is we don't care about the radius at all, really. That's actually remarkable, actually, okay? So you're bound only considering the argument, not the angle, not the magnitude, the complex number at all. It's shocking to us, actually.
But like since the Poly theorem is kind of invariant under rescaling.
But then hold on. That's right. But then there can be ratio between the
Ratio, yeah, right.
cannot depend on either, okay? So, I'm saying that if you only use the angles, okay, of the complex roots, this would be optimal. You can do that. So this is it, okay? So I'm not going to talk about the proof of any of these things right now. It's technically involved. Okay?
So can the angles be computed?
How to compute the angle? No.
Right.
Actually, we estimate.
Okay.
There should be also we have right now large estimation with estimation.
And the 3 is based on your estimate or on?
Oh, that 3 was exactly computed. That's why in this case. That's why. Your questions I understand. What if your estimation gives you 4,000? That's your question. It doesn't. I think it's about 5.
Okay.
Okay, so I think I will stop here. Is it okay with you?
Yes.
By the way, this work is ongoing, okay? There are many questions, by the way. I'll just finally, I'll just make my final drop some words, okay, here. The work I present to you has some certain connections to what they call positive Stellensatz. Is the Hilbert Stellensatz applied to the positive Stellensatz? Okay, and also in other words, also connected to what? Hilbert 17th problem, actually. However, this result is actually what? It should be viewed as a refinement of that thing, meaning it gives you more information than the positive Stellensatz. Otherwise, I'm not working on it. It gives you more information than this. That much I will say. Okay, I finish the talk. Thank you. Yes.
Like, could you clarify in
By the way, from now on, if I go over the time, all because of questions like this, okay? I'm not to be blamed.
So,
Continue. Okay, go ahead.
in which sense does it give more information than positive Stellensatz? Because they solve the same problem.
Yeah. So, okay, the point is basically, if you look at it, okay, unlike Hilbert Stellensatz, okay, you have the sum of the squares, right?
Mm-hmm.
That thing is a problem. Here, I don't have anything like a sum of squares. So sum of squares gives you, because sum of square, you cannot turn things into linearize. You cannot linearize it. Hilbert Stellensatz, okay, you can linearize it, okay? But positive Stellensatz, you cannot linearize it because it's square term.
Mm-hmm. Okay, thank you.
But this one, you linearize it.
So regarding the prolongation method,
By the way, this is not my prolongation method. I'm just multiplying by variable. It's age old.
yes. So for that age-old prolongation method,
That's right.
what is the bound for several equations, several variables, etc.?
Yeah, this is a terrible right now. Okay, that's why I show you right now. Okay, so it's terrible bound. Okay. Very complicated also. So I'll clean up first. Is it okay with you?
Okay, but this case is already meaningful enough.
You're asking whether this case means univariate case?
Yes,
Yes, of course. In this case, it's got a lot of consequences actually already. Univariate cases, okay. So that's why I still think that I do not consider univariate cases over. Here, still there are a lot of questions to be answered, to work with. Okay. So for instance, checking this for the comparing the what positive Stellensatz relationship to the univariate case is already interesting. Okay, so there must be still explored. Does that answer your questions? Right? Yes.
But like, if I have such a system of linear equations in positive numbers, how easy is it solve it? How hard?
You mean system or what?
System of linear equations,
Yeah, this one.
But we've constrained that all solutions should be positive.
Whether this is harder? That's your question?
How much is harder, for example, than just solving linear systems?
You mean over partial real?
Yeah.
Partial real, that's right. Okay. So now you're asking me a question which I cannot answer it because it's not my domain. But from now I speak without confidence. I heard from my colleagues it's easier with this guy actually. That's what I heard. Now how they solve the case when this is positive? Well, then they actually into select variables so-called, and then they turned into actually the two variables. They double the variables to work over the arbitrary real numbers.
Okay.
So actually, from that point of view, this is easier. Yes.
So suppose you know that there is an x.
Yes. Yes.
Is there a way to find the minimum solution?
Minimum solution. Okay, that's a good question. How can you? So let's go through them. Okay, first of all, let me go back to the complex case. Okay, complex root case. Okay, so now it's the prolongation relaxation can decide whether it exists a common solution or not. Question is, if it exists, can you find the solution? Right, somehow approximate. That's your question, right? If it's complex, the same with the real also.
For complex, there's no maximum, but for real, you can talk about minimum and maximum, or minimum at least.
You're right. Complex cases, can you find all the solutions, let's say? And actually, that's possible. You go to the prolongation relaxation scheme, okay? And then you get a linear algebra problem, and you do some more massaging there, you can turn it into an eigenvalue problem. Now, some background story. This is not a contribution from this area I belong to, symbolic computation. It's actually a contribution from a numerical analyst, an Austrian guy called Hans Stetter. He's a well-known numerical analyst, and he felt bored with his work in numerical analysis, so he decided to venture into symbolic computation. So he came along and discussions, and he learned about something called the Grabner basis method. Okay, and then one of the key symbolic computation method, and he realized that this is terrible numerically. So he tried to fix this problem, turn it into an eigenvalue problem. Okay, and there's some technique, and technique can be applied to over complex. So you find the eigenvalues, eigenvectors. In fact, eigenvector gives you all the coordinates for all the solutions. Okay, over here. You cannot turn it into eigenvalue problem over real. Okay, you cannot. So what you can do is that this is something which I'm discussing again with the numerical people. They're saying that this basically numeric projections is basically the numeric projections. Okay, and what happens is that if you look at if you relax this guy, then you get basically what you get some set in the R square, and you look at this guy. You get a set, it defines a set. It's a complex set in the R cube, okay? So you have sequence of this set in the ever higher dimension. But if you consider projection onto the what? X1, then that set, the projection shrink as you prolongate, shrink, and then into an interval. It becomes interval, and then the low bounded interval, it is the minimum. Yes?
How about inequalities?
The same thing happens.
Same thing.
Yeah, the same thing happens. There's no difference.
Okay, some more questions? Thank you.
Okay, thank you so much for being with me.